you think about the complexity and the difficulty in this. What you're looking at is, even with the nearest star system to us, with Proxima Centauri, and we've now proved that there's exoplanets orbiting pretty much most stars. I mean, it's 1 in 10 from telescopes like Kepler, which has been in orbit, and looking at these transit events where what happens is a planet will pass in front of the star and the light from the star will dip due to the planet basically passing in front of it. So larger the planet, the bigger the dip, etc. If you've got multiple planets, you'll see multiple dips. So that's one method. The other method is using spectroscopy, where you're looking at spectral lines and you can see changes in the spectral lines and shifts in the spectral lines caused by the gravity of orbiting planets. So, interesting methods, both of them. But from an optical standpoint, even at the nearest star system, which is just over 4 light years away, recognizing that something, the Earth, for example, could be swallowed up by the sun a million times. So it's a million times, the sun in terms of its mass is a million times larger. So if you had a small planet the size of the Earth orbiting in front of the sun, and you were trying to look at that from 4 light years away, now don't forget 4 light years, you've got 186,000 miles per second. There are 86,400 seconds in a day, 365-ish days in a year. And then times that by 4.3. And essentially, that's how many miles you're talking about to the nearest star. And these stars outshine and are far brighter than anything else in their vicinity, obviously, because planets don't have natural light of their own. They just use the reflected light from the star. So even detecting this, which was first done in the 1990s, and we've now got over 4,000 exoplanets in our own galaxy, is an incredibly difficult challenge, but one that even amateur astronomers are now able to do. From the back garden telescopes. We've got a decent sized back garden telescope. You can take part and see these light curve dips because the quality of cameras, etc., is getting so good. So this detection, however, was using an X-ray or a combination of X-ray telescopes. This was the Chandra telescope run by NASA and XMM Newton, which is run by the European Space Agency. And if you want to see one of those, XMM Newton, if you go to the Toulouse Space Centre in France, if you ever get a chance to go there, they've got a full-size model of the XMM Newton out in the grounds there. So it's a big telescope. Now, the thing about X-ray radiation is that it's at the kind of higher end of the frequency spectrum, so shorter wavelengths, etc. And technically, therefore, you should be able to get more precise observations. It's still incredibly complex, but what this team did, based at the Harvard-Smithsonian Center for Astrophysics Research, what they did was they pointed at M101, M104, M51, 3 relatively nearby galaxies, and they were looking for these dips, and they found one. So this planet is known as M51 ULS1b, snappy name as we know. Really, really remarkable discovery using this transiting method. It's hopefully going to open up observations of a plethora of extragalactic or, pan-galactic, but extragalactic exoplanets.